All right, and we are back. We had a little interlude there with the fire department, but we're we're safe and sound now and back. We were talking about thalidomide, different enantiomeric forms of it. One can be a cause of birth defects. The other can be a good sleeping pill. Problem was, it was initially marketed and sold as a racemate, a mixture of the two enantiomers. Now it's got problems there. But chirality, we'll have to get into this. This idea of handedness or asymmetric, no internal mirror plane, and identifying four different ligands on the group. It has to do with reactivity. Sometimes we go from achiral molecules and create chiral molecules. We have to analyze this here. So let's go to the board. Well, there's some examples of drugs. A lot of stereocenters. Actually, some are achiral. The sulfa drugs, aspirin, are achiral. I believe all the others here are chiral. No. Xandy here at the bottom, that's also achiral. Oh, and sildenafil is also achiral. No stereocenters. So you often see the solid wedge or the dash here, but you have to analyze it. If there's a carbon with four different groups on there, that's kind of the key here. So let's start with isomers here on the board. I'll look at different isomeric forms. And we've actually had how many types of isomers? If you've been keeping track, let's see. How many types of isomers have we talked about? Who can think of one type? Yeah. Yeah, so constitutional or structural isomers, and that has to do with different order of bonding. So that would be what? Butane and 2-methyl propane. Those are constitutional isomers, okay? Very good. We've talked about a couple other forms, actually. Yeah, who's got another one? Cistrans or stereoisomers. So here we have cis 1,2-dimethyl cyclopentane, and here we have trans. Okay, and we'll have to look at these in a little more detail. It'll turn out that these are stereocenters. One of these stereoisomers is actually achiral, one is actually chiral. Okay, we'll get back to that, but it's a little more detail. Right now, we just talked about stereoisomers in the cis-trans sense. Cis-trans also applies to alkene isomers oftentimes. If we have two different groups across of an alkene, we also call that trans. This is 2-butene that we'll see later on. We'll do the naming of alkenes and whatever later, but 2-butene is a trans isomer, and this is 2-butene also, but the two methyls on the end are what? Cis to each other. So that's also forms of stereoisomerism. What about this? Anti-butane versus what's this form here? Gauche or eclipse butane? Are those isomers of each other? What did we call those? That's another type of isomerization, right? What are those? Not constitutional or stereoisomers. It's just rotation around the sigma bond. Those are what? Conformational isomers. Okay? And that's just rotating around the sigma bond. Okay? You can't isolate these two and separate them. They don't have different boiling points or melting points. These are just different rotational states of that same molecule. But indeed, this image is a conformational isomer of that one, just like the two ring-flipped chair forms of cyclohexane, okay? So that's actually three. Well, let's look at another here. How about this? Let's have this form of an alcohol. I'm drawing that stereocenter there, this carbon here, with the hydroxyl group bold. This is 2-butanol, okay? And let's look at this form of 2-butanol. Well, these are both 2-butanol. Now, we'll learn the naming of alcohols later, but you see I changed the E on the end to an OL group. That's now, the parent is still butane, but the suffix here reflects the functional group. We're not formalizing that IUPAC naming for alcohols yet. That'll be coming up in a later chapter. But we're just pointing out these are both 2-butanol, but what's the difference between the two? They're not conformational isomers. They're not structural isomers. They're both 2-butanol. They're not stereoisomers. They're not cis-trans, are they? But this right here is indeed a stereocenter, okay? And what this means is that one stereocenter means the molecule can exist as two enantiomers, okay? This is one enantiomer form. We'll see that this is indeed the S enantiomer. This is the R enantiomer. And what enantiomers mean is that they're mirror images of each other that are not superimposable. And that seems kind of strange, but if you take this structure and superimpose it or try to lay it right on there, you'll see that you can get the butane fragment here, the parent structure, to coincide, okay? So the butane parts are congruent here. But look at the stereocenter here. So this one, the S form, has this alcohol coming out, and look, the R form has that alcohol going back. So the two other ligands here, the hydrogen and the hydroxyls, are not congruent. They're not superimposable, okay? So hence they are enantiomers, two different forms here. So this idea of handedness and chirality. So let's back up a little bit and think about some common physical objects that might be chiral or achiral. How many sports people do we have out there? Any baseball or softball players? Probably a few. Or have you at least played softball or baseball? Okay, this goes back a few years for me, but I still have some nice mitts. Okay, and I'm, what, a right or a left-hander? Can you tell right away? Am I a righty or a lefty? Can you tell? My mitt fits on my, what, left hand? And I'm throwing with my right hand, right? So you can tell I'm throwing from the right side, okay? And what the mitt I need to use has to fit my left hand. If I were a lefty, would this be good? Let's see. Oh, it doesn't feel right. Oh, my thumb's way over here, and my other four fingers are jamming over here where the thumb usually is. So it kind of has the same overall shape, but that's a bad feeling, right? It's not going to work. So baseball mitts are inherently chiral, okay? The ball itself is achiral. You have mirror plane symmetry here. Unless the guy is a curveball thrower, then it's got an inherent spin that's coming at the batter from a different direction. Oh, speaking of the batter, is the bat chiral or achiral? Is there an internal mirror plane in that object, that bat? Yeah, okay, it's symmetrical, it's barrel shaped or whatever. How about when the batter takes a stance at the plate? Is that position of batting either from the right side, which I would do. If you're a switch hitter, you can go over to the left side and bat. But there's an inherent, what? Dissymmetry there, right? On the left or the right side. Any other sports or musical instruments, or any other physical objects you can think of that either chiral or achiral? What can you think of? How about a mug, a cup? You can use that equally from the left or the right side, right? That wouldn't be chiral, that'd be an achiral object. How about scissors? Any lefties out there? Any left-handed people? Okay, there's always at least one. And sometimes scissors are just for right-handed people, right? Okay, nowadays they make scissors that people can use them from either side, but that can be a problem. How about sitting in these chairs in the position of the writing table? That the most of the chairs are made for right-handed people, be on the right side, and lefties sometimes have a problem. They got to reach over and write from the other way. So there's all sorts of objects this way that can come up. How many golfers do we have out there? I know there are some that put down golf as their hobby or interest on the questionnaire. And there, the golf clubs are for righties specifically, and normally are. If you're a left-handed golfer and go to a golf course and try to rent clubs, guess what? It's probably unlikely they're going to have a set of lefty clubs for you. That's because the club heads you're hitting from the other side are going to be just a little bit different. So this idea of chirality is actually all over the place. You're probably just not aware of it. In fact, it's in science and a couple other places. In physics, maybe you've heard of the right-hand rule, the direction of angular momentum, for example. You can see it in art, and a lot of artists are very aware of what they're coming in from the left or right-hand side. It's in literature. Anybody read Lewis Carroll's books? What was he famous for? Through the Looking Glass. And that was the adventures of who? Alice in Wonderland, the bizarro world that was the mirror image, right? So we've got this idea all over the place. So chirality, what does this mean chemically? And what do we mean on molecules here? So chiral, or handedness, okay, means non-superimposable mirror images. And we'll get into that a little bit more with examples, but chirality, it also means lacks what? Mirror plane. And by mirror plane, we mean an internal mirror plane, okay, within the object. So hopefully the things we talk about gives you a little bit of a feel for that. Achiral means that they are superimposable. And what are we talking about? What are we superimposing or non-superimposing? We're talking about the mirror image, okay? So the mirror image of a chiral molecule will be not superimposable, okay? Whereas an achiral object will be superimposable on its mirror image, okay? So let's get into this. So how about this molecule here? Let's start really simple and go through the operation of symmetry with it. So what are we talking about? Water. Is water a chiral molecule or is it achiral? Well, let's see. If we held that up to a mirror, what would it look like? It would look like this. Oh, you'd say, oh, it's the same thing, right? But be careful. We're going to get to chiral molecules or it's not. If we take this image here and superimpose it, what do we get? They're completely congruent, okay? So that mirror image object of the original object is superimposable. So what do we conclude here? Chiral or achiral? Achiral, okay? So it has an internal mirror plane. You can see where that mirror plane is right in the middle of the molecule. The two hydrogens on opposite sides are the same. That bisects right at the atom position, okay? What about this? And what molecule is that? That is indeed methane. Is methane a chiral molecule? Well, hold it up to the mirror, okay? And what do we mean in the mirror? If we looked at the image here in the mirror of this, what would it have? It have this. So yeah, I'm drawing, these dashes and wedges. And now we need to take that mirror image object and what? Superimpose it on here. So we need to rotate it around, what, 180 degrees. You see we'd have hydrogen, hydrogen, and hydrogen, hydrogen. So when this superimposes, are all the atoms congruent and everything? Yes. So is methane chiral or achiral? Achiral. Very good. Okay. So put AC there and make sure you understand what that means. All right. I'm going to get a little more complex here. How about dichloromethane? Methylene chloride. Chiral or achiral? Well, you can already see here, for chiral, we're going to need carbon with 4 different ligands. Okay? And you can already see in methylene chloride, we have 2 ligands that are the same. We have 2 hydrogens that are the same. So you can already kind of surmise here that what? It's going to be achiral. But let's go through the test just to make sure. Plus, there's an internal mirror plane right here through the middle of the molecule. But let's see, what would be its mirror image look like? It'd look like this. Hydrogen coming out there. Chloride, the top, chloride in the plane right there. You see we could take that, rotate it around, and put that right on top of the original structure. And that would be congruent. It would be superimposable on its mirror image. So therefore it's what? Achiral. Okay. Now let's do this one. Let's do bromo, chloro, fluoro, methane. Any guesses here? Is bromo, chloro, fluoro going to be chiral or achiral, and why? Any guesses? Someone's got to be brave enough to chime in here. Please, go ahead. Chiral, because it's 4 different ligands, and we can test this, how? By seeing if it's superimposable on its mirror image. So let's go with Alice through the wonderland, through the looking glass. Anybody read those books anymore? I tried to get my kids to read them and they didn't like them. They're a little too weird. Okay, yeah, Alice in Wonderland. Read that sometime if you want. And so what do we get? Chloro here coming back. Got fluoro in the front, hydrogen, and bromo. Everybody agree that that is the mirror image of that. Let's make sure we got that clear. Okay. Now let's rotate, what, 180 degrees. We'll get bromo here. So this is this image rotated, right? So I'll bring chloro in the front and fluoro in the back. Can you guys verify that and make sure that's what we did there? So we took this object and just rotated it around. And you see the bromide rotates over here. The hydrogen's still in the top there. And chloro comes around here in the front. And fluoro rotates around in the back right there. Does that look right? Okay, let's take that object and superimpose it here. What do we get? Hydrogen, bromo, chloro, and fluoro. Now, if we superimpose these two images, or two enantiomers, let's use the right term, we see that they're not congruent. They're not superimposable. Why? The bromide, the carbon, and the hydrogens are all superimposable. But what's out of congruency here? What's not overlaying? The chloride overlaying with the fluoride. You see fluoride's in front. Here now chloride's in front. And now fluoride's in back, chloride's in front. In fact, that's how you can draw the two enantiomeric forms. If you have a stereocenter with 4 different groups, you can just exchange any two, and you'll get the opposite enantiomer. Let's look at the models here and make sure that we're doing this right. So what do we have? Hydrogen here, which is black, bromo, purple, red is fluoro, and there's chloro, okay? What would be its mirror image? It'd be this. Okay, so physically engage with these models and make sure you can see that. Is that the mirror image? Look, yeah, purple's over here in my right hand. Purple is way over here to begin with. If you held this up to a mirror and looked at it, you'd see this. Okay, this is the mirror image. And let's try to superimpose them. What do we get? Okay, black with black's okay, purple, purple. But look, yellow with red and red with yellow. Look, they're out of congruency. So these are the same constitutional isomer, right? These are both bromo, chloro, fluoro, methane, right? But they're two enantiomeric forms because this is indeed a stereocenter, okay? Let's see if we can take one and this one, and we already identified that these are enantiomers of each other. Let's see if I can get this back to being this. Take off any two groups and just exchange them. So this is sleight of hand. I used to work as a magician in Vegas. This was part of my lounge act, doing this. No, okay, it was not. Okay. But let's see the trick here. Only organic chemists appreciate this, but let's see. Are these indeed these are the same now, okay? Because look, they're right on top of each other. All of them are congruent. So these are the same. Okay. Let's see if we can get it back to enantiomers. And I'm not going to look. I'm just going to randomly pick any two. It doesn't matter which two. As long as I put them back the opposite positions, I should be back to what? Being enantiomers, right? Let's see if we got that. Purple back here. Yeah, okay. Now they're enantiomers, and look at that. Not congruent, not superimposable. Red and yellow are out. Okay, so do this trick too. Amuse yourself and your roommates by going through this. See if they appreciate that. That'll help you lock in this idea of having it there. So let's try one with 3 different ligands here. How about if we try this one? Do we really need 4 different ligands? Let's see. How about hydrogen, chloride, bromide, bromide? So here's dibromochloromethane. Let's look at the mirror here. And what do we have? Bromo, bromo, hydrogen, chloro. Is that the mirror image? Yeah. And let's rotate this around 180 degrees. We'll have hydrogen here. We'll have chloride there. And look, bromide will be rotated around to the front. And yeah, bromide, rotate around to the back. Can you put that right on top of the original image, and are they superimposable? Yes. So what do we conclude about dibromochloromethane? It is indeed achiral because it is superimposable on its mirror image. Let's go back to the alcohol. How about bromo or 2-butanol? What would its mirror image look like? Look like this. You'd say, well, it looks like the same thing, Dr. Andrews. You've lost your mind yet again. No, that is the mirror image, right? This is coming out right here. This is this methyl down right here, and then the ethyl group over here. Well, let's rotate this guy around to see if it will be indeed congruent. It'll look like what? This. And as we rotate it around, what will happen to this? The hydroxyl will be in the back right here, okay? And this hydrogen will be in the front. And now when we try to overlay that, what does it look like? Yeah, there's that idea that we just pointed out, right? They're not congruent. The OH and the hydrogens are different. So 2-butanol, we say, is chiral, okay? What about an alkene? Now here, an alkene, these carbons just have a hydrogen, a carbon, and a carbon. They don't have 4 ligands to begin with. And let's verify this. Its mirror image would look like what? Look like that, right? And you could just take this and flop it over, and it'd go right on top of that, okay? Really see that? You just take that and put it right over here. And you see this is completely congruent. There's no carbon with 4 different ligands here. So this is what? An achiral molecule, okay? Cannot exist as a pair of enantiomers. All right, let's see. What about this one? We showed this example. What would its mirror image look like? It would look like this. Is this the mirror image of that? Yes, it is. And what? You could take this and just put it right on there. So cis dimethyl cyclopentane, chiral or achiral? It's achiral, okay? We'll see that we can actually identify stereocenters here. We can assign R and S. But why is it achiral? It has an internal mirror plane symmetry. And when that reflects through the mirror, if it has this internal symmetry, you'll get this image, which will actually be the same thing as this. It will be superimposable, it will be achiral, okay? And this last thing, real quick, sorry, went a little bit over. Let's look at the trans form of that. What if we had this? And let's look at the mirror image of that. And that's just the stereoisomer, the trans dimethyl, right? And so what would it look like? Look like this. Ah, is that the mirror image? Yes, it is. And if we try to superimpose that, take this out here and lay this right on here. Look at this. Look at this. The cyclopentanes are superimposable. But look, the methyls, one's up, one's down, one's up. These are not superimposable now. So this is the tricky part. If you think you've followed it so far, make sure you practice this and look at some of the examples here. This is indeed chiral. Can exist as 2 enantiomeric forms. We'll help ourselves out by assigning R and S next time and keep track of this, but we'll have to end it there. Sorry about the fire drill and everything. 10 minutes shorter time here on the video today. We'll pick it up on Friday, okay? Very good. We'll see you then. Thank you. Okay.